Swayam Prabha. Digital India. Educated India.
Welcome to the first lecture of module 2, which is on CAD models for additive manufacturing. In this lecture, we shall discuss about the solid modeling, brief introduction, CAD modeling particularly for additive manufacturing, and then the very important file format which is very popular for additive manufacturing, STL file, we shall discuss in detail. We shall discuss about its introduction, data structure, ASCII format, binary format, resolution, deviation tolerance and its angular tolerance. So first is solid modeling. Solid models are known to be complete, valid and unambiguous representation of an object. A complete solid is one which enables a point in space to be classified relative to the object, if it is inside, outside or on the object. A valid solid is one that does not have dangling edges or faces. An unambiguous solid has one and only one interpretations. The completeness and unambiguity of a solid model are attributed to the fact that its database stores both its geometry as well as its topology. So what is geometry and what is topology? You are seeing two objects here, one here and another here. In this case, both the geometries are same, but their topologies are different. Geometry means the length of the line L1, L2, L3 are same as in this image L1, L2 and L3. Also the radius R is same here as radius R. Definitely there is a arc C1 and here also there is a arc C1. The only difference in these two geometry is the center of this circle, whether it is outside the object or it is inside the object. You can see that if it is outside the object, there is a concave shape, and if it is inside the object, then it is convex shape. Just a minor change in the topology, you can see that the final object is different. This is an example of same geometry but different topology. Now look at this example where the geometry L1, L2, L3 are different as you see in this diagram. The relation between L1 and L2 is different. Here it is not 90-degree angle, while here in this case it is 90-degree. Although the topology is same, you can see even this point is placed outside the object, but different geometry. So this is an example of same topology and different geometry. There are four popular methods of representing a solid. First is called as constructive solid geometry, CGS, CSG, boundary representation, BRAP, feature based modeling, FBM and space decomposition, ST, and a combination of more than two of the above may called as hybrid modeling. Nowadays many packages uses this hybrid modeling. I will give you one example. The SolidWorks is based on something called as feature based modeling, while they do not really use much of the constructive solid geometry. Let us try to understand the difference between the four different strategies of representing the object. The first one was CSG, constructive solid geometry. If I want to represent this particular object by utilizing this strategy, then I will select the basic primitives such as the cubes, cylinders and all available with the CAD package. So for example, if I take this cuboid like structure, which is definitely available as a primitive in a CAD package, and then another basic structure that is a cylinder. The difference between these two objects will give you nothing but this object. So in CSG, we basically perform the Boolean operations between the standard shapes available with the CAD package to realize or represent the complicated objects. The another strategy which is called as boundary representation or BRAP. In the BRAP, the solid model is represented by its surfaces. So for example, what you are seeing in this particular object, there are 7 surfaces. One is this is second, there is a surface here, that is 3, there is a surface here, that is 4, this surface is 5, and from the bottom side also there is a surface that I am calling as 6, and this cylindrical surface 7. A collection of these surfaces appropriately means which is defined by the topology can represent this solid object. So basically we need to have the surfaces like 1, 2, 3 and 4, that is nothing but the rectangular plate or rectangular surface, and then surface available on bottom and top side, that is nothing but your 5 and 6, and then a cylindrical surface. Appropriate location of these surfaces together, which is defined by the topology, can represent the object we are seeing here. This is called as boundary representation. Next is feature based modeling. In the case of feature based modeling, we utilize some of the features available with the CAD model or the CAD package. These features could be like extrusion, revolve, sweep and all. So for example, if I want to make this particular object, first I will draw a sketch, and then this sketch can be extruded. The extrusion of this sketch will give you this particular object. In the case of FBM, the Boolean operations are basically inbuilt. You need not to perform the Boolean operation explicitly. Another is SD, the spatial decomposition. The next is SD, that is the space decomposition. In that case, we basically define the domain like we define in 2D plane through pixels. Here, those unit cells are called as voxels. So basically, a collection of tiny cubes will represent this particular model. Appropriately, they will be connected with each other. Where there will be no material available, there will be hole. So the appropriate collection of these voxels when utilized to represent the solid model is called as space decomposition, and this particular representation is called as voxel based representation. However, there are few other methods also for space decomposition that you can refer further. Different CAD packages uses different schemes like I already discussed. They may be using the CSG, BRAP, FBM, SD or hybrid for representing the solid models. Theoretically, any commercial package or any scheme can be used to create the solid model of the object. However, most of the CAPP platform of additive manufacturing machines require the solid model of the object in a format called STL. And all these commercially available CAD packages are capable of converting the solid models into the STL format. The example of the same has been shown here, where SolidWorks is used to convert the solid file or the solid model into the STL file. So for that, in the case of SolidWorks, you go to file and save it as STL file. So the STL file is basically derived from the word called stereolithography, which was the first commercially available additive manufacturing process produced by a US based company, 3D Systems, in 1980s. Over the period of time, STL is also known as Standard Triangle Language and Standard Tessellation Language. However, the original name of STL was derived from stereolithography, where this is ST and this is L. The STL format encodes a surface geometry of 3D object using the simple concept called tessellation. That is why over the period of time, like I said, the format is also known as Standard Tessellation Language, STL. What is tessellation? Tessellation is the process of tiling a surface with one or more geometric shapes such as there are no overlaps or gaps. You can see a very practical example, a tiled floor or wall at your home. So, for example, this is the wall which is tiled by the triangular shape plates. This is a flat surface, while this is an example of a curved wall which is approximated by these flat tiles or flat plates. I will show you one real life example of STL file. This is an approximation of a sphere. You can see that the outer surface or the boundary of this object is represented by the triangles, and hence it is not a very accurate representation, but approximately it represents the object. So, STL is a faceted boundary representation basically of the model that approximate the model surface by connected series of triangles. It does not contain any information related to color, texture or density inside the material or inside the object. An STL file describes a raw unstructured triangulated surfaces by representing each triangle by a unit normal and 3 vectors. So, the each triangle of the STL file is represented like this. It consisted of 3 vertices. Here you can see P1, P3 and P2, and a corresponding unit vector which is representing the on which side the material is and on which side there is no material. Usually in the direction of the normal there is no material, and in the opposite direction there is material available. Usually these vertices are ordered in such a way that if I apply the right hand side rule, I can represent its normal. There is no material available in the direction of normal, like I already mentioned. It is an example of representing a complicated surface with large number of triangles. You can see that if the number of triangles are increasing, we are able to represent the object more accurately. However, the size of the file will also get increased. Now, there must be a question why we should use triangles. There are certain characteristics in the triangle that makes working with it simpler and faster. Any 3 non-collinear points form a triangle. This is the very fundamental of a triangle. Every triangle form a unique plane. Triangle points cannot be part of 2 planes, which save us from the trouble from dealing with multiple solutions. What you are seeing here in this diagram, for example, if I represent a surface or a flat surface by utilizing 4 points. So, in that case it is basically a quad mesh. Now, you can see that if somehow I move this point wrongly, then definitely this portion will represent a different flat surface and this portion will represent a different flat surface, and hence the contact normals will also be different. This is another example when I am representing it in another direction, and hence your contact normal will be again different. So, therefore, triangle points cannot be part of 2 planes, which save us from such conditions. Any surface can be broken into the triangles, and triangle can only be broken down into further triangles. Therefore, triangle is used as a unit entity to represent the surface of an object. So, mathematical equation of a triangle surface, it is very easy, but it is right time to understand it. If I have a point on a triangle which is represented by x, y and z, and there are 3 vertices, those are x1, y1, z1 of the triangle, x2, y2, z2 and x3, y3, z3. Now, if this point is lying on the surface of the triangle, then I can say that these 3 vectors are collinear. 3 vector means the vector connecting this point to this point, I mean this vector, then this vector and this vector, right. these three vectors are going to be coplanar. If these three vectors are coplanar, then definitely I can say that the determinant of this particular matrix will be 0. I'll utilize this rule and I'll find out the implicit equation of this surface. Now let me give you an example. The question is to find the equation of a plane in the vector form that passes through the point 1, 1, 0, 1, 2, 1, minus 2, 2, minus 1. First of all, we shall check whether these 3 points are collinear or not. If they are collinear, definitely a triangle cannot be formed in this. If they are not collinear, then definitely a triangle can be formed. To check the collinearity of these 3 points, it's very easy. You just put these points in this manner in a matrix and find out its determinant. If the determinant is non-zero, that means these 3 points are not collinear. Now let us use this equation which we derived to find out the equation of this surface. These are the 3 points. I'll replace this by x1, y1, z1. This is x2, y2, z2. This is x3, y3 and z3, and I'll put in this equation, and hence we will get this equation for the surface. So this is how a triangle can represent a surface. Now let us come back to the STL file and discuss about its data structure. The content of an STL file is a set of oriented triangles, each described by the following numerical data. Those are the NXI, NYI and NZI. These are nothing but the coordinate of the outward normal of a facet. Now these are the 3 vertices. As I am talking about the ith triangle or ith facet, the I term is written here. It will be consisted of 3 points, of course. That's why this particular nomenclature is used here, 1, 2 and 3. And this is the x coordinate, that is why x is written here. This is y coordinate, y written here, and this is z coordinate, z is written here for 3 vertices. Once again, where the NXI, NYI, NZI are the coordinates of the outward normal of ith triangle, and PKXI, PKYJ and PKZK are the coordinate of kth triangle, are the coordinate of kth vertex, where k is nothing but 1, 2 and 3. There are 3 vertices in a triangle. The triangle can be any number. Therefore, if there are n triangles, then I will be equals to 1, 2, 3 up to n. The STL file does not contain any information related to the topology, such as links, pointers or another elements such as proximity. Each vertex is written by its coordinate in the file as many times as it occurs in the mesh. This fact may cause some problem with the vertex identification depending on the numerical representation of real numbers. Also, the file does not store the dimension units. There are 2 possible formats for STL file. Either it can be in ASCII format, that is nothing but the text format, which is human readable format, or it can be in the binary format. Of course, the ASCII format is more user friendly. Why user friendly? Because one can easily read the ASCII format, while the binary is more system friendly, because the size of the binary file is relatively less as compared to the size of an ASCII file. How does an ASCII file looks like for STL? It starts with solid and the name of the object which we are creating or name of the file. If I am creating a sphere, I am writing here a sphere. So solid is sphere. Then a facet normal is given, and adjacent to facet normal 3 coordinates are written. These are nothing but your nx, ny and nz. This represents, the facet normal represents the outer normal or outward normal of the facet or the triangle. Next, there is a loop which starts with outer loop and ends like AND loop. In between, there are 3 points those are representing the triangle. So, these are the three vertices of the triangle, vertex 1, vertex 2 and vertex 3. If it is first vertex, then I should write it like this: P1x, this is nothing but P1y, this is P1z. In a similar fashion, this will be P2x, this will be P2y and this will be P2z. This will be P3x, this will be P3y and this will be P3z. The group of three vertices defining the triangle is determined by the term outer loop, you remember that, and it ends with the end loop. Finally, the definition of the facet and with and facet. So, this represents the whole thing from here to here is representing the entire triangle. If there are n triangles, n such lines or n such loops will be written. The vertices of the triangle are listed in counterclockwise manner, so that by using the right hand rule one can find out the direction of the facet normal. With this proper structure of the vertices, even the data corresponding to the triangle normal is redundant. What I meant to say, I will explain again. This is the triangle, and if this is the point P1, this is P2 and this is P3. They are arranged here also, like this is P1, this is P2 and this is P3, in a manner that if you start from this point, you can draw a circle like this. So, these points are written basically in counterclockwise manner. If we use now our right hand side rule, we will find that the contact normal is nothing but outward. One can notice, if I have the information of P1, P2 and P3, I can even calculate my normal vector easily. Therefore, this information available with the file is going to be redundant. We shall discuss about it in more details. How can we find out the contact normal of a triangle if the three vertices are given to us? Let me consider the three vertices here. This is P1, its coordinates are x1, y1 and z1. This is P2 and its coordinates are x2, y2 and z2. This is P3 and its coordinates are x3, y3 and z3. Let me form a vector A, which is x2 minus x1, this is the vector I am defining, A vector, x2 minus x1 I, y2 minus y1 j and z2 minus z1 k. So, this is the vector I have defined. Now, let me define another vector B connecting the point P3 and P2. If I define it like this, then the vector B can be written as x3 minus x2 I plus y3 minus y2 j plus z3 minus z2 k. Therefore, now I can find out the contact normal of the triangle. So, this facet normal n will be nothing but the cross product of these two vectors A and B divided by the magnitude of this cross product, and hence I will have the unit vector in the outward direction. It is very simple. Now, A cross B can be written like this. This is A and this is B, and the cross product of these two can be written in this form. It is nothing but the determinant of I, j, k, x2 minus x1, y2 minus y1, z2 minus z1, x3 minus x2, y3 minus y2 and z3 minus z2. Now, let us try to solve a problem. In the given triangle of an STL file, show that the facet normal data is redundant. So, we have to prove that. So, what we will do, we will utilize these three vertices and find out its unit vector. If that unit vector by utilizing only the vertices is coming to be the same as given here, then it is of course that one of these information is going to be redundant. Here, let me identify, this is your x1, this is your y1, this is your z1, x1, y1 and z1 corresponding to the point P1 of the triangle. Then this is x2, y2 and z2, this is corresponding to the P2, x2, y2, z2. and then there is a P3 here, and corresponding points are X3, Y3 and Z3. X3, Y3 and Z3. Now I can easily find out A cross B, and hence the A cross B is coming to be as 30,000 I plus 0J plus 0K. The unit vector of the same, the unit vector now can be find out, unit vector in the direction of outward direction of the facet normal will be n equals to, or n cap equals to A cross B divided by magnitude of A cross B. We have already find out A cross B, this is A cross B, and its magnitude is going to be 30,000. If we divide it, nothing but we are getting I, or I can write it in the component form like this, 1, 0, 0. Now let us check with this. You see that the facet normal given here is 1, 0, 0, and what we have also got is 1, 0, 0. Therefore, this information is redundant. Now let us write a ASCII code for representing the cube of side 1 unit in STL format. This is the cube, and let us assume that the Cartesian coordinate system is aligned like this. Means the origin of the Cartesian coordinate is here. That means this particular vertex will be assigned to 0, 0, 0. As there are total 8 vertices, 4 on the bottom side and 4 on the top. The coordinates for these vertex will be given like this. Now to represent this cube, we need 12 triangles, because each rectangular face of the cube will be consisted of 2 triangles. And please note that these 12 triangles will represent the cube exactly. Means even if you increase the number of triangles, the accuracy cannot improve, because it will be the exact representation. As there are total 6 faces and each face is consisted of 2 triangles, total 12 triangles will be required. This is going to be the first triangle. Let us write the code for representing this triangle in the ASCII format. First we shall write the facet normal. The facet normal of this triangle is going to be in this direction, that is nothing but minus y direction. Hence the facet normal is written as 0.0, minus 1.0 and 0.0. That means this particular term is representing the facet normal is in the minus y direction. Then we shall write the outer loop corresponding to the vertices, and it should be in order which is representing the directional or the facet normal. Hence it should be in counterclockwise manner. So this is the counterclockwise manner, that this arrow is showing the counterclockwise direction. Now we shall write the vertices starting from left, and then this, and then this. We can start anywhere, but this order should remain same. We should not write like starting from this point and then this point and then this point. It is not a feasible way of writing it. If you want to write in counterclockwise, let us start from here. Hence first vertex is 0, 0, 0, 0. The next vertex is 1.0, 0, and 0.0. Then the next vertex is 1, 0, 1. Then we will end the loop and end the facet also. So one facet is completed. Now this will be the second facet. In a very similar fashion, in this facet also, the contact normal is in along the y direction, minus y direction. Hence the facet normal is written as 0.0, minus 1.0 and 0.0. The outer loop corresponding to the vertices is written here, which is representing the vertex 1, that is 0, 0, 0, and then the next vertex 1, 0, 1 and 0, 0, 1. The order of writing this vertex is again in the counterclockwise manner, and this arrow is representing the same. Hence we are starting from this point, then this point, and then this point. Reverse of it is not a feasible idea. Now let us write the ASCII code for this particular triangle. Here the facet normal is now along the y direction, positive y. Hence we need to stand. It has to be assumed that we are standing here and then observing the triangle. And when we are observing the triangle from here, the counterclockwise direction will be this. You can visualize it. And hence now the triangle should be written in this manner. Those are, the first one is 0.0, 1.0 and 0.1, sorry 0.0, that is this particular point. Then after that I can write only this point, that is 0, 1, 1, 0, 1, 1, and then after that 1, 1, 1, that is 1, 1. Now in a very similar fashion for this triangle, where the facet normal is along the direction of 0, 1, 0 along the y direction, positive y direction, and in a similar fashion the counterclockwise direction will be this, because we are assuming that we are standing here and watching the triangle. Then the vertex will be, if the first vertex is written 1, 1, 0, then second will be 0, 1, 0, and the last will be the 1. Now for the top side, this particular triangle, it is having the contact normal in this direction or facet normal in this direction. Hence it is 0, 0, 1. 1 means along the z direction. Then the three vertices. First vertex is this 0, 0, 1. Then to follow the counterclockwise direction manner, we should go for this point, that is 1, 0, 1, and then 0, 1, 1. Similar fashion, this particular triangle will also have the same contact normal or facet normal, which is 0, 0, 1, and hence by following the counterclockwise direction, we can write the vertices. If we are starting from 0, 1, 1, then next will be 1, 0, 1, and then next will be 1, 1, 1. Now for this particular triangle, now we can see that the normal is downward, that is why minus is written here. Hence the facet normal is 0, 0, -1. Now observer is standing down here and observing above, and then it will look like that this particular direction is showing the counterclockwise direction. Hence if we are starting from point 1, 1, 0, then next point will be 1, 0, 0, and next point will be 0, 1, 0. In a very similar fashion, we can write this particular triangle, that is also very similar, and the direction normal is downward, that is in -1 direction. Hence 0, 0, -1. The three vertices are 1, 0, 0, and then next will be 0, 0, 0, because we need to follow the counterclockwise direction, and then next is 0, 1, 0. Now let us consider another triangle here, and this is representing the counterclockwise direction. Its facet normal is in +1 direction. Hence the facet normal is 1, 0, 0, and vertex is, if we are starting from 1, 0, 1, then next will be 1, 1, 0, and next will be 1, 1, 1. Similar fashion, we can write the ASCII code for this particular triangle. This is the direction for counterclockwise, and facet normal is same for this triangle as well. It is in +x direction. Hence 1, 0, 0. The vertices 1, 0, 0 here. Then this is 1, 1, 0, and then next is 1, 0, 1. Now in a similar fashion, this particular triangle, now we need to be careful because observer is standing here, and when he is observing from this end, the direction of the counterclockwise direction will look something like this. Hence if we are starting from point 0, 1, 0, next point will be 0, 0, 0, and next will be 0, 0, 1. The facet normal is of course in the -x direction here. Hence the facet normal is written as -1, 0, 0. Now this is the last triangle, and the facet normal is again along the -x direction. Hence it is -1, 0, 0, and the loop representing its vertex if we are starting from 0, 0, 1, then we need to move in counterclockwise direction. Next point will be 0, 1, 1, and next point will be 0, 1, 0. Now all the triangles, if we write together in the ASCII format, the code for cube will look something like this. We are starting with a solid cube A, then copy pasted the definition of each and every triangle. As there were 12 triangles, you can see there are 12 such loops. 1, 2, 3, and like this there are 4 columns. 1, 2, 3 and 4. Hence there are total 12 triangles. Now let us copy paste this data in Notepad++ and save it as STL file and see whether it works. So now let us copy this data and paste it in a text file. Then we shall save this text file as STL and then we will see whether we have really created a cube or not. So let us copy this data. I have already started the Notepad++, which is a text editor. You can use other editors as well. Paste your data, then corresponding to the other triangles. And the last group of triangles. Make sure that your code ends with and solid and it starts with solid and the name of the solid. Here I give a name as cube A, means cube is my object and A stands for ASCII format. Now once I pasted my data in a text editor, I can save this file and I will give a name to this file as same cube A dot STL. So you have to write this extension manually because it may not be available as a default extension in the text editor. So let me save it now. A file has been created here. Its name is cube A. Now it is an STL file. If I now double click on this file and open with the default software which I have assigned to such files, that is Descartes, you can see the cube has appeared. This is the wireframe model of the cube. If I switch on the triangulation model, you can see that this is your cube. This is the boundary representation of the cube. All the triangles are nicely available here. That is why you are not able to see any such defects in that. You can see the triangles also. So these are the triangles which we have defined and saved in the text file. So this is how you can create a cube by writing your own code in the ASCII format. You can use the same analogy to write the code for any object. Now let us discuss about the binary format of the STL file. If the tessellation involves many small triangles, the size of the ASCII STL file will become very large and hence a more compact binary version of the format is desirable. A binary STL file can be described in the following way. First of all, an 80-byte ASCII header that can be used to describe the part is used. So 80 bytes are used to describe basically the name of the object or name of the file. Then a 4-byte long integer is used to indicate the total number of triangles in the object in the beginning. So 4 bytes are used to define an integer which represents the number of triangles. Then a list of facet record, each with 50 byte long, is used. So each triangle is represented by 50 byte long data. What is that? How this data is distributed? 3 floating values of 4 byte each are used to describe the normal vector. That means there are 3 floating values, right, to define the facet normal. This is your n1, this is n2 and this is n3, x, this is y, this is z. And each are consuming 4 bytes. That means total 12 bytes are required to represent the contact normal or the facet normal. In a similar fashion, 3 floating values of 4 byte each are required to describe the first vertex, and in similar fashion to represent the second vertex and third vertex. Hence 12 bytes will be required here, 12 will be required here and 12 will be required here. So total 48 bytes are required to represent the normal and 3 vertices. Then one unsigned integer of 2 byte is used that should be 0 and it is used just for checking purpose. So 2 bytes are used for that. So total 50 bytes. This is how the 50 bytes of each triangle are used. So 50 bytes into n. If there are n triangles, then n such bytes will be required. That if you sum it off, then you will find out 84 plus 50n, that should be the size of your file. Now let us see, if you create a STL file of a cube which looks something like this, it is consisted of 12 triangles. We have already discussed that. Now this is how a binary file looks like. You can also look a binary file by using this open source. You go to this website and drop down your binary file which is created by the CAD package, then you will see this type of data. Now let me try to explain to you how the bytes are assigned. So 80 bytes are used to define the name of the file. So in each line there are 16. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So there are total 16 lines here, and if you count up to this point, there are total 80 bytes used just for defining the name of the file. Then after that, like I said, 4 bytes are used to represent the number of triangles. So 0C in the hexadecimal, if you convert this hexadecimal to decimal, you will find that this 0C0000 is nothing but will represent 12. Then the data related to the facet normal starts. The first 4, this one is showing nothing but your contact normal or the facet normal. This is 0000803F. This is a hexadecimal float number. This is hexadecimal representation of a float number. You can convert this to decimal by utilizing this particular link. So you go to this link, copy paste this hexadecimal data, and you can see that what is the value of this data in the decimal form. Then these next 4 are representing the another component of the normal, and these 4 are representing the another component of the normal, and you will see that it is something and then 0 and 0. Then these 4 bytes are representing the x coordinate of vertex 1, these 4 bytes are representing the y coordinate of vertex 1, and these 4 bytes are representing the z coordinate of the vertex 1. In a similar fashion, then these 4 are for the x coordinate of the vertex 2. In a similar fashion, the entire file is structured. To convert these hexadecimal numbers to decimal, you can utilize the library available in the coding platform which you are going to use, such as Python or in Visual Studio. It is easily possible to convert these numbers. In total, like I said, there should be 80 bytes for the header, 4 for the number of triangles, and then 50 into 12. 12 is the number of triangles, because we know that it's a cube and there are total 12 triangles here. Multiply 12 with 50 and hence total 684 bytes are to be used to represent this cube. And you can see that if you count this, there are total 684 bytes. So this is how a binary file of the STL file look like, and if you want to manipulate this file or read this file, you can do that easily by utilizing the platforms like Python or Visual Studio or MATLAB. Now we shall discuss about the STL resolution. This is the exact representation of the object. In this case, the boundary of the object are represented by the nonlinear curves such as NURBS and splines. While we said that we used to convert this data into STL file, and in that case the collection of triangle will represent its boundary now. This is a coarse representation of the object and this is a fine representation. You can see that the number of triangles here are 2000 352, while the number of triangles here are 6162. The file size also you can see is increasing. Since an STL file approximates the part surface geometry using tessellated triangles, there is a trade-off between the accurate representation of the curve and number of triangles we use. Larger the number of triangles, larger the file size, it is obvious. Most CAD software allow to control the size of triangles and hence print quality and the file size. Let us explore these parameters to achieve the optimum value. First is called as the deviation tolerance. It is the maximum deviation between the designed part and the STL file. The maximum deviation between the designed part and the STL representation of the part. It is represented by a parameter called chord height or deviation tolerance. The chord height is the maximum distance from the surface of the original design and STL mesh. So what you are seeing here in the green color is the original, and what you are seeing here in black color is the line corresponding to the STL file or after tessellation. So the maximum distance between this original CAD geometry's edge and now the tessellated geometry edge is called as nothing but the chord height. If the right tolerance is chosen, the printed part will look more smoother, and it's quite obvious that the smaller the chord height, the more accurate the facet representation, the actual surface of the model. It is recommended to set this particular tolerance between 0.01 to 0.001 mm. This usually results in good quality prints. There is no point in reducing this further because your 3D printing or the 3D printing machine itself may not provide this much accuracy. Now let us consider this example. How many triangles will be required for deviation tolerance to be 0.05 mm to represent a circle of 100 mm radius by STL format? So now we have a circle which is represented here in the green color, and now we are representing this circle by these triangles, 1 triangle, 2 triangle, 3 and like this, so on. This distance can be easily calculated. If there are n such triangles, then this angle will be nothing but 360 by n, and half of this angle will be nothing but 360 by 2n. Also, this length, if this is r, radius of the circle, then this will be nothing but from here, from this point to this point onwards, this length will be this much length. From here to here, it will be r cos 180 by n. Now, this particular length, which is called as chord height, can be calculated by subtracting this length from r. So, r minus r cos 180 by n will be nothing but this length. Now, this length is what they are asking us to keep as 0.05 mm. So, we will do nothing, we will just equate this with 0.05. After solving it, we will find that the value of n is to be coming around 99.39, which is to be considered as approximately equals to 100 triangles. So, n is equals to 100. That means 100 triangles will be required to represent this particular circle or the surface of this particular circle. I have verified this answer by utilizing the software SolidWorks. You can also do that. While saving your file, while you save it as STL file in the property, you can put the deviation tolerance as 0.05, and then you will find that the total triangles will be 400. Why 400? There will be 100 triangles on the top surface, on the circular part, 100 on the bottom and 200 on the periphery. Why 200 on the periphery? It is obvious that each triangle which is formed like this will converge like this on the periphery, and then it will converge like this. So, each triangle will correspond to 2 triangles on the periphery of the cylinder. Therefore, there will be 200 triangles here. Total 400 triangles. That means our calculation is perfect. This verifies our calculation towards the deviation tolerance. The another type of tolerance is called as angle tolerance. It controls the maximum angle between the normal vectors of each triangle. The smaller this value, more dense the tessellation of the curved surface. It increases both resolution and file size. The recommended setting for this parameter is as low as possible. Now let us try to understand what is it. So for example, we are representing this curved surface by the triangles, and that will be nothing but there will be some edges over here, and these are the contact normals on these edges. That will be nothing. For example, they are forming a triangle on the bottom side somehow like this. Then the angle between the contact normal of these two triangles is nothing but angle tolerance. This is nothing but theta here. Now let us try to solve a problem for angle tolerance. The question is, how many triangles will be required for angle tolerance to be 1 degree to represent a cylinder of 100 mm radius by STL format. So this is the cylinder you are seeing. The green color boundary is representing the exact boundary of the cylinder, and this black color boundaries are showing the triangulated edges of the cylinder. Now, what is first of all the angle tolerance? It was discussed earlier as well, the angle between the two consecutive triangles. So, for example, if you see the triangles on the top surface, the contact normal of each and every triangle will be vertical, and hence the angle between these two contact normal or facet normal is going to be 0 degree. Now, but these triangle, those are representing the periphery of the cylinder, this bottom one, these triangles will be at a different angles. Now let us consider two consecutive triangles. So as we discussed in last example also, there will be two triangles corresponding to one triangle on the top. So this is one triangle, and correspondingly there are two triangles you can see. One is this and another is this. Now let us try to find out the angle between the two consecutive triangles. If you see, these two triangles will be having 0 degree angle between them because the facet normal is same. It is basically nothing but forming the same plane. But the facet normal or the angle between the facet normal of this triangle and this triangle will be different. So the facet normal of this triangle can be represented by a line connecting the center line of this, because that will be nothing but the facet normal, and hence the same vector I am drawing here. In a very similar fashion, the facet normal of this triangle will be represented by this line on the top, and hence the same I am representing here. The angle between these two will be nothing but this angle, and we know that if there are n triangles available on the top surface, then the angle between the two triangles will be 360 by n. Hence, if 360 by n is equals to 1, that is the requirement, because the angle tolerance should be 1 degree. Hence, n will be 360. So, total 360 triangles will be required here on the top. So, if the number of triangles will be 360 on the top surface, then on the bottom surface there will be another 360, and on the periphery twice of 360 triangles will be required. Then total triangles will be 4 into 360, hence 1440 triangles in total. For this particular example, please note that for this particular example we can see the number of triangle is independent of the r. There is no r here. That means whatever the radius of this circle is going to be, or the cylinder is going to be, the number of triangles will remain same if you want to keep that angular tolerance of 1 degree. I have done the same in SolidWorks, and I change the circle diameter. In this case, the cylindrical object's radius is 100 mm and the angle tolerance is set to be 1 degree. You can see the number of triangles I got are 1440. When I change the radius, and if it is now 1000 mm diameter of the cylindrical object, still the number of triangles are same. This is because this particular equation is independent of R. You can also try uh, this example by using a CAD package and keep the angle tolerance 1 degree for a cylindrical object. For any radius, you will get the same answer. So now let me show you the same thing with the help of a CAD model. So this is the CAD model of a cylinder, and you can see, like I said, each triangle on the top making two triangles on the periphery. You can observe that carefully. Now you can also see, if I look at the ASCII code of that, these are the some triangles on the periphery, because if they are the triangles on the top or bottom surface, their facet normal will be like either 001 or 00-1. But there are some numbers here, that means these are the triangles corresponding to the periphery. Now you can observe here, if I'll just take this example, this facet normal is same as this facet normal, and this facet normal is same as this facet normal. So let me delete the other triangles for time being. And then open the file. Let me reopen the file now. And you can see now there are only 4 triangles. Now there are only 4 triangles, and these 2 triangles are having same facet normal, and these 2 triangles are having same facet normal, and the triangle this and this are having different facet normal, and that is what we try to solve in the problem. Now we can consider one line over here and one line corresponding to here. Wherever they'll join on the back, that will give you the angle between these 2 facet normals. And if you consider project this on the top surface, it will be nothing but the angle between the 2 facet normal will be nothing but 360 by n, where n is the number of triangles on the top surface. Now let us discuss the problem which we have solved, where the angle tolerance was 1 degree. So this is how that object looks like when I kept the angle tolerance 1 degree. There are very tiny triangles. Now I need to identify the 2 consecutive triangles on the periphery where the angle will be 1 degree. We need to verify that. So let me go back to the part and open it with the Notepad++, and I'll just select these 4 triangles here. As the facet normal is not 001 or 00-1, definitely these are not the facet normal on the top or bottom surface, they are definitely on the periphery. Here you can see that the facet normal of this triangle and facet normal of this triangle are exactly same. That means they are in the corresponding to the one triangle on the top surface on the periphery. Now these are the 2 triangles corresponding to the another triangle on the top surface and on the periphery of the cylinder. Now let me consider all these 4 triangles, and my objective will be to find out the angle between this facet normal and this facet normal, and it should come as 1 degree. So those 4 triangles were copy pasted here, and you can see that these 2 are having the same facet normal and these 2 are having the same facet normals. Now my objective is to find out the angle between the facet normal of this triangle and facet normal of this triangle. It can be easily done by using the dot product. We know that the dot product between the 2 vector will give us, like if you want to find out the cos theta, it will be nothing but A dot B divided by magnitude of A, magnitude of B. As they both are unit vectors, these magnitudes are going to be 1 only, hence I need to take only the dot product. So the dot product is written here, theta equals to cos inverse. This is the this is the product between the x component and this is the product between the y component. The z component is 0, hence it is not written here. And finally, you will have your theta equals to cos inverse 0.9998476,238, and hence your theta equals to 1.0002342. So you can see that it is approximately close to the answer, that is 1 degree. Why we are not reaching to the exact value? This is because I have considered few places after the decimal, while in the code it was up to the 15 places after the decimal. If I considered all, I should have get the exact answer, that is 1. Now let us discuss about the topology rules in the STL file. The first rule says each edge in the triangulation is shared by at most 2 triangles. The edge cannot be shared with more than 2 triangles. I'll just show you this example through this physical model also. You can take any edges. This edge, it is shared by this triangle and this triangle. This edge is not shared with triangles more than 2. You can take any example of the edge on this solid. The second rule, which is also known as the vertex rule, it states that each triangle must share 2 vertices with its neighboring triangles, which is also known as knot to knot property. A vertex in the triangulation can be shared by any number of triangles. So let us consider this physical example again. This vertex, it is shared by multiple triangles. So it can be shared with as many as possible triangles. The next rule in the topology states that, which is also called as the orientation rule, the orientation of the facet, that is which way is in the 3D object and which way is out of the 3D object, must be specified in 2 ways. First, the direction of the normal should be pointed outward. Second, the vertices are listed in counterclockwise order when looking at the object from the outside by utilizing the right hand side rule. So it means if you have a triangle in the STL file, its outward normal in such a way that on this side there will be material and on this side there will be no material. Also, the same normal can be calculated by applying the right hand side rule. So if this is first vertex is written, this is second written and this is third, then I can even find out this facet normal by applying the right hand side rule also. The fourth rule states that each triangle has at least one point in common with another triangle. It is also called as connectivity and requires at least 2 triangles. The last rule for the topology is no triangle should have an intersection with the interior of any other triangle. It is quite obvious, like if you have a triangle like this, the another triangle should not intersect it like this. In that case, these type of cases are also called as the manifold edges. Now let us discuss about some mathematical errors. The computation of the line of intersection of 2 surfaces can lead to error in knot to knot connection vertex shared by the triangles lying on the different surface. So what you are seeing here is one example of the same. This vertex is lying on this surface, this vertex is lying on this surface, and this is the common point. This common point supposed to lie on this surface or on this surface, but due to the error in defining the floating numbers, this vertex may be considered on this surface or on this surface. Second one is raising the accuracy of the computation may not really help. In contrast, due to higher tessellation resolution, smaller triangles are generated and triangles may collapse into a line whenever one of its side becomes too small. So, for example, you want to increase the computation and hence you are keep on increasing the number of triangles. So, for example, in this triangle I will further divide it into like this, and then further I will divide it like this, further I will divide it like this. You see that in the end this small edges, this vertex has become so close to the another vertex that this edge will just vanish, and hence what you will have is nothing but a simple line. Also, the third mathematical error which usually occur in the STL file is high degree edges can be generated and shared by more triangles, particularly at tangential positions like you are seeing in this diagram. So, usually these mathematical errors arises because of the float point numbers. You are defining the same vertex multiple times, and when you are recalling these vertices for any further operation, it may be possible that the vertex may not be called at the same precision. Also, sometimes you will see the errors like this. For example, there is a vertex which is shared by multiple triangles. And this is a common vertex. Due to the error in the float point number, this vertex may not be having the same value when called different times, and hence there will be an opening here. This portion will get open. It will look something like this. Something like this. So, this portion will get open like this. Also, you can see the same error when we are trying to join, because we have, when we made this model, we just collectively made the triangle first and then try to join them. As the error accumulated, you can see some of the vertices are not really joining and there are holes in the model. The same error propagates due to the mathematics involved in the STL file. Thank you very much.